Hello, everyone. In this session, we are going to look at degrees of freedom. Degrees of freedom of a gas. Now, in kinetic theory of gases, as well as in thermodynamics, you would see that degrees of freedom for a gas is mentioned again and again. What does that mean? How to deal with that? How is that related to the adiabatic constant? That is what we are going to see in this session. Degrees of freedom, it simply means the number of ways in which a molecule can move. When we talk about gases, we have different types of gases. We have monoatomic gases like helium. We have diatomic gases like hydrogen and oxygen, H2 and O2. We have triatomic gases like ozone, carbon dioxide, CO2, carbon dioxide, and so on. Now, each of these different gases, each of these molecules will have a different number of degrees of freedom. And that is what we are going to count. Let's get started with monoatomic gas. A monoatomic gas is a gas which has one atom alone. So if you talk about one spherical atom like this, think about how many different ways this atom can move. So this atom can only move in a 3D space. That means it can either move in the X direction, it can move in the Y direction, or it can move in the Z direction, coming out, okay? Let's use this to indicate the Z direction. So these are the three ways in which this small atom can translate. So we would say degrees of freedom, but translational degrees of freedom for this monoatomic gas is 3. It can move along the x-axis, it can move along the y-axis, and the z-axis, 1, 2, 3. So 3 translational modes. What about rotational modes? The rotational modes for this would be considered 0. The reason being, the moment of inertia for this atom is very, very small because the radius is very, very small. So we would say that no rotational degrees of freedom for this. Vibrational degrees of freedom for this is again considered 0 because vibrational degrees of freedom only come into picture when there is a stretching or contraction or change in length of the bonds, okay? Or there is angle change between the bonds. One atom, no bonds at all, we cannot talk about vibrational modes. So vibrational modes 0, rotational modes 0, translational modes 3. So overall, we can say that for a monoatomic gas, the number of degrees of freedom is just 3. That means there are 3 different ways in which this atom can move. Let's look at a diatomic gas now. Let's take oxygen, for example, and we are going to count how many degrees of freedom will this gas have. So we have one oxygen atom, double bond, another oxygen atom. So this is the molecule. This is the oxygen molecule, okay? O2. These are oxygen atoms, and there is a bond between the 2 atoms. In how many different ways can this entire molecule move? Translational is going to be the same. It can move along the x-axis, along the y-axis, and along the z-axis. So 3 translational modes of degrees of freedom, or 3 translational modes, or 3 ways in which it can translate. What about rotational modes? Ideally, there should be 3 rotational modes. See, now we have a bond, and the bond length is much, much larger than the radius of this. Since the distance between the 2 atoms is bigger compared to the radius, so it will have a significant moment of inertia now. So if we talk about the rotational energy, it will have a significant rotational energy because I value would be significant. When we talk about rotation, we would talk about rotation about some axis, right? So let's take those axes. One would be the x-axis, okay? So if the molecule is rotating about this axis, something like this, the atoms are going like this, okay? About this line, about this line. That can be one way in which it can rotate. What can be the other way? Other way can be about this axis, okay? The molecule is going round and round like this, okay? As if, so here is your molecule, one molecule here, one atom here, another atom here, and it's going like that, like a fan, okay? So that can be one way to rotate. And the third one can be about the z axis. So if this is our axis, this molecule will go round and round like this. These are the three ways in which it can rotate. And yet, we say that there are only two rotational degrees of freedom. Why is that? Because I about the y-axis is significant. We are going to count that. Moment of inertia about the z-axis is also significant. We are going to count that. Because what is it is? It is mr square, or where r is the distance from the axis to the mass. So if I'm calculating the moment of inertia, it's going to be, since these are spheres, it's going to be 2 by 5 md square, where this is d, plus 2 by 5 md square, right? Significant value. Same thing for Iz, significant value, because the distance in question is much, much larger than the radius. However, if we go and try to calculate the value of Ix, it's just going to be 2 by 5 mr square for this molecule, and once more we'll add that plus 2 by 5 mr square, so it will become 4 by 5 mr square. But notice here that this r is actually very, very small compared to this d, and that is why we ignore this. Okay, we ignore this. So two rotational degrees of freedom. How about how many vibrational degrees of freedom? So usually at room temperature, in order to excite it vibrationally, a lot of energy is needed. So at room temperature, we would say vibrational excitation does not take place. This change in bond length, either stretching or compression, does not take place. So for diatomic atoms, for diatomic molecules, for diatomic gases, we would say that the vibrational degrees of freedom are 0. So total degrees of freedom for a diatomic molecule is how much? Is 3 plus 2, 5. Okay. Let's now look at triatomic molecules. Now, triatomic molecules are of two types. One is a linear triatomic molecule and the other is an angular triatomic molecule. Something like CO2 versus H2O. CO2 would look like this. It's a linear molecule, okay? Entirely, it's like this. However, H2O, it's going to be a bent molecule because there are lone pairs of electrons. Yeah, okay, which is going to bend this. So there is an angle here, right? These two types of triatomic molecules will have different number of degrees of freedom. Let's first focus on the linear one. Linear triatomic molecules. We'll do this quickly, okay? Translational is 3 along the x, y, and z axis. Rotational will be 2, okay? And vibrational, it can have vibrational degrees of freedom. Let's now talk about the vibrational degrees of freedom. Vibrational degree of freedom is given by the formula 3n minus 3 plus 2, which is 5 for a linear triatomic molecule. 3n because all the three atoms, this oxygen, this carbon, and this oxygen, are free to move in 3 dimensions. That means x, y, and z. So 3 for this, 3 for this, 3 for this, total 9. 3 into 3, that is 9. This is the number of atoms in a molecule. So 9 minus 5, 4 vibrational degrees of freedom are possible in this. Now, it depends on the temperature, okay? So if the temperature is really low, not all the vibrational degrees of freedom will be excited. So maybe only 1 vibrational degree or 2 vibrational degree is excited. So this you would be given in the question, how many vibrational degrees of freedom have been excited for this, at what temperature? Okay. So overall, this is the situation. At room temperature, however, for a linear triatomic molecule also, F vibrational at room temperature would be 0. So overall, the total number of vibrational degrees of freedom at room temperature for a linear triatomic molecule is going to be 5. Okay. What about a non-linear triatomic molecule? For a non-linear triatomic molecule, translational is 3 along x, y, and z axis. Rotational is again 3. Okay. About this axis also, there is significant moment of inertia. About this axis also, there is significant moment of inertia because this distance will come into picture. And about this axis also, the axis, there is significant amount of moment of inertia because this distance will come into picture. Okay. So it has 3 rotational degrees of freedom as opposed to a linear triatomic molecule, where Ix was 0. But here, Ix won't be 0. Okay, so that's why we now have 3 rotational degrees of freedom for this one. So at room temperature, how many degrees of freedom? You would say total degrees of freedom is F total is 6 at room temperature. Now, if you increase the temperature, vibrational modes are going to get excited, and the number of degrees of freedom for vibrational mode, total number of degrees of freedom would be given by 3n minus 6 this time. 3 plus 3, 6. So there are 3 atoms, so we would say 9 minus 6, so 3 vibrational modes are possible in this case. You can see, though, these are the 3 vibrational modes. Okay, one is the molecule is, so let's say this is oxygen, this is hydrogen, this is hydrogen. The hydrogen atoms are bending and stretching. Okay, bending like this, like swinging like this. That is one mode. The other mode is asymmetric stretching and compression of the bonds. So it's like this. These are the 2 hydrogen atoms. One is going like this, the other is going like this. So something like this, something like this. And then there is symmetric stretching and compression of the bonds. The third vibrational mode is it's going like this, going like this, like this, like this. Okay. So these are the 3 different ways in which a triatomic nonlinear molecule can vibrate. And that is why the maximum number of degrees of freedom for the vibrational mode is 3. Okay. This was all about counting the number of degrees of freedom of a molecule. Monoatomic, diatomic, triatomic, and so on. But how is it related to specific heat capacity or the adiabatic constant? Let's take a look at that. From kinetic theory of gases, you would know that CV, or specific heat capacity at constant volume, is given as F by 2R. What is that F there? That is our degree of freedom. Okay. So Cv is this. Can you tell me what Cp would be? We all know Cp minus Cv is R. So Cp is R plus Cv. That means 1 plus F by 2 times R. This is your Cp, right? So we have Cv, we have Cp. Now, can you tell me how to get adiabatic constant gamma from Cp and Cv? Gamma, or the adiabatic constant, is the ratio of specific heats at constant pressure versus specific heat at constant volume. So Cp upon Cv. Let's see what we get. RR is going to get cancelled. We get 1 plus F by 2 upon F by 2. You solve this, you get 2 by F plus 1. This is your gamma. This is how the adiabatic constant is related to the degrees of freedom of a gas. Let's now use this concept or use this logic to solve a previous year question which has appeared in one of the state boards engineering entrance exam. The ratio of molar specific heats of oxygen, the ratio of molar specific heats, that means they're asking Cp upon Cv. Why not Cv upon Cp? Why did I say they're asking? Ratio can be Cv upon Cp also, right? As you can see here, all the ratios are more than 1. That means the numerator has to be bigger. And that is why I can confidently say that they are asking the value of Cp upon Cv, which is also called gamma, or the adiabatic constant. Anyway, oxygen is a diatomic gas. We know that. So how many degrees of freedom for this? Degrees of freedom, 5. If those many degrees of freedom are there, can you say what would be the value of gamma? It's 2 by F plus 1, 2 by 5 plus 1, 7 by 5, 1.4. So this would be your answer. Okay. This is how you can calculate gamma for any gas. You don't need to remember these values. Yeah. For carbon dioxide, you can calculate because it's a linear triatomic molecule. For H2O or water vapor, you can still calculate the gamma. Okay.